Welcome to my session. It's called Mirror First Blue-Green Deployments with Octopus and Istio. And for the beginning, I want to just take you through the agenda. First, we're going to hear a little bit about me, and then we have a theoretical deep dive a bit. We are going to answer the question, what is a service mesh? Also a short reminder to what blue-green actually is before we then get to my core of the talk, my mirror first or the mirror first approach. Before we then go over to some gotchas and some key takeaways, and then answer the question, what else can you do with the service mesh? And then we have a little bit of QA time planned. I'm not sure if this is going to be needed, though. Okay, so first about me. My name is Felix Notka. I am a senior cloud consultant at Pexon Consulting GmbH in southern Germany. And you can see me on the right at KubeCon London 2025, along with a lot of really cool Octopus people, and I'm the person with the blue jacket in the middle. Why am I the person in the blue jacket? Because I am a CubeSonaut, and many of you will be probably asking, okay, what is a CubeSonaut? It's a program that the CNCF launched at KubeCon 24 in Paris, and there are currently approximately 2,650 CubeSonauts worldwide, of which there are 153 in Germany. In order to become a CubeSonaut, you have to hold 5 certifications at the same time, which are the Kubernetes and Cloud Native Associate, the Kubernetes and Cloud Native Security Associate, the Certified Kubernetes Application Developer, and the Certified Kubernetes Administrator, as well as the Certified Kubernetes Security Specialist. And you can see here all of the CubeSonaut who attended the same KubeCon in London in 2025 on stage, and all of them have cool blue jackets. But on that same KubeCon, the CNCF launched a new program, which is called the Golden CubeSonaut. There are a lot fewer people who have this title, approximately 200 worldwide, exactly 19 in Germany. And on top of the 5 Kubernetes certifications that you need to hold, you need to have 10 additional Kubernetes certifications. And you can see here the list. There's stuff that's quite theoretical, like, for example, the Certified GitOps Associate or the Certified Cloud Native Platform Engineering Associate, which deal a bit more in concepts. And you have exams which focus on tools around the Kubernetes ecosystem, like, for example, the Prometheus Certified Associate. And when it was launched, a couple of people asked me, oh yeah, Felix, are you going to do the Golden CubeSonaut? And I said, no, not really, because and my argumentation back then was, I don't need to use a service mesh. In my mind, a service mesh was something that only really big companies use, with a lot of clusters, with a lot of complexity. And that's honestly way too much for me and my projects that I've had so far. And as you can see here, the first exam on this list is an Istio Certified Associate, which is a practical exam. It's supposed to be extremely difficult. And I was like, no, not really. I'm perfectly fine staying just a regular CubeSonaut and having my Kubernetes knowledge. And yeah, as maybe you can see a bit ahead, that didn't stick. About 3 weeks ago, I became the 17th Golden CubeSonaut in Germany. And it took a while. It was really interesting. It was a lot of certifications and exams. But some of you may ask the question, okay, why though? What really changed? And to be honest, it just started when I typed into Google, what is a service mesh? And service meshes are an incredibly interesting concept, which you can do a lot of stuff. And in my talk, I hope to show you a little bit of it and give you a taste for more, but there's definitely more stuff that you can do with it. But to explain it, a service mesh is a dedicated infrastructure layer added to a Kubernetes cluster to manage, observe, and secure communication between microservices. It does so by automatically placing a tiny lightweight proxy alongside every single application container. Most of the time, that's an Envoy proxy. That's a small little application that's written in C++ and developed by Lyft a couple of years ago, and it's incredibly performant and incredibly cool. But these proxies intercept the network traffic entering and leaving the services, and they manage the data flow without the application even being aware that they exist. And the whole goal of a service mesh is to try to decouple the business logic from the network logic and ensure that security, reliability, and observability are applied uniformly across the entire cluster. I also have a small little diagram here, and this is basically the way that pod-to-pod communication, very simplified, works in a native Kubernetes cluster without a service mesh. So you have on the left container A, and container A wants to talk to container B. And in order to achieve that, container A goes ahead and basically pings the service B. And the service B is sort of like a router and a load balancer. And the service B strictly just goes ahead and says, okay, I have a request here that came to me, and it wants to connect to a pod that's, for example, labeled app equals container B or something like this. My absolute favorite analogy here, which I think most of us can absolutely relate to, is to imagine yourself back in school. And imagine yourself that you are a pupil and you are container A and you want to talk to your friend, which is container B. But in the middle of you, there's a person who's new at school, that's our service, and it's his job to sort of forward the message. So back in the day, you had a piece of paper, you wrote your message on, and then you folded it in half and wrote the name of the person you are trying to reach, in case you're a friend. Let's just say the friend is called Mike or something. So you as container A have your small little envelope with the name Mike, and you pass it over to service B. And service B, the person in the middle who doesn't really know anything, is looking to the right and checking, is there a person named Mike that is supposed to be container A's friend? And if so, I'm going to give him the node. And with that analogy, I think we can all spot a little bit of issues here. For example, what happens when, I don't know, someone who's not supposed to read the message just comes along to service B and says, oh yeah, hey, I'm Mike, you can give me the message as well, because service B will forward this message, and this is a bit troubling. Also, as container A, you have no idea if your message really connected to where it's supposed to go. You have no idea how long it took and which path it took. And so a bunch of really small people have gone ahead and have created a service mesh. And the diagram that I'm showing you right now is a bit complicated, but with that analogy, I think we can get through it quite easily. So the goal is still the same. We are a container A, and we want to talk to container B, which is our friend. And because it's almost Christmas, we can say that the school has a special exchange program where magical little elves appear. And these magical little elves all of a sudden come to every pupil in the school and tell them, hey, I'm a messaging elf, and I will take over your complete communication via messages. And in the school also there is sort of the brain of the whole elf agency, which configures them and tells them what to do. So instead of you passing the node to service B, you go ahead and while you do that, so the application thinks it's still targeting service B, the elf comes along and takes your message, and then the elf will look up the person you're trying to reach. So for example, as I said, your friend Mike, and will then connect to your friend Mike. And it does so not directly to him, but the elves, your friend's elf will intercept this message as well, get the message, and then forward it to your friend. And the good thing with these small little helpers is that we can teach them a lot of stuff. And because they are centrally managed, we can tell them, okay, for example, you want to be in encryption and you want to have MTLS support. Then all they would have to do is take your message, put it inside a big metal bag, and then carry it around to the elf of the person you're trying to reach, where they then could check their certificate, and if it's really the person you're trying to reach, and then decrypt this message. Or for example, these helpers could go ahead and could write stats about how many times they went from you to whatever friend you were trying to reach. And this is incredibly helpful for observability, for security, and for reliability. And as we can see here, and to recap, the goal of a service mesh, or a major benefit of a service mesh, is to decouple the business logic from network logic. It lets developers focus on features, meaning communication between you and your friends, while the helpers focus on stuff like security, authentication, authorization. It's also incredibly helpful to allow you to have uniform observability. Since the helpers can automatically gather metrics, logs, and traces across the entire cluster, it's not really that important which tech stack you're running, and you don't need to focus on every single application. Also, as I've said, zero trust security, major thing in Europe right now with NIS2, and service meshes are a good part to get started with that. But with that, you can enforce uniform security policies and encrypt traffic between services. You can also go ahead and tell your applications to only receive traffic from these amounts of, or from these specific entities, and only to send out to specific entities. And you can have a little bit of fun, which is the advanced traffic control. You can do precise data flow management, including canary deployments and circuit breaking. And this is what I will show off later a bit. But basically, we can tell our helpers, if I get a message and the person who sent me this message is my friend Steve, then I need to handle it differently than if it were any other friend. So when should we actually use a service mesh? The most common use case is for complex microservices, because then you can offload network logic like retries and timeouts from the code to your infrastructure. Also, what I've said just now, the polyglot environments. If you have different applications with different teams managing them, and all of them need to go ahead and learn about and implement very specific language SDKs, then that can take a huge amount of time. But if you can have a centralized observability strategy, and every package of traffic that is sent across your whole cluster can be logged or configured in a specific way that you can see it afterwards, that just alleviates a lot of pressure from the teams. Also, if you have strict security guidelines, if you want to have MTLS support throughout the whole cluster without really doing any code changes, or if you want to have an authorization or authentication policy cluster-wide, that is also really, really helpful. And the last part is for advanced releases. So we can have the traffic shifting like canary and blue-green support directly at the network layer instead of outside on the load balancer level. But we will see all that a bit later. And first off, I think we have to have a small course through what are exactly blue-green deployments. Even though we've heard it fantastically before a couple of minutes ago, I unfortunately need to repeat that because it's in my talk. First, blue-green deployments is a deployment strategy that uses two identical productions environments, blue and green. And blue in this case is the current one, and green is the idle one. A new application is deployed and tested in the green environment, while blue continues to handle the user traffic. And once green has been verified, a load balancer switch comes along and just reroutes the traffic from blue to green. And this means we have almost no downtime during the deployment, and we can switch back and roll back really, really fast. But after a successful deployment and after it's been tested, green becomes the current one and blue becomes idle. We can see that in this diagram as well. So we have user traffic hitting our production environment through our load balancer, and our load balancer routes all traffic to the blue instances, in this case V1. We have an idle application instances stack, application V2, this is green, but this is not used anywhere. They both share a lot of resources like the database, because only one of them is supposed to be active at once in a blue-green environment. And after we've checked everything, we can just switch the load balance around and have AppV2 user-facing, and the blue instance is now the idle one and can then be used for example, application version 3. And we can have this exact diagram just a little bit more technical with our service mesh. So in this case, we have user traffic hitting our Kubernetes cluster, and the ingress gateway will then take the traffic and route it to 100% to the blue instances and to 0% to the green instance. We have our control plane, which configures all of that. And this is nothing else than basically this diagram, just a little bit more technical. And the same works for if you want to switch traffic around. Then we only have to configure the ingress gateway configuration, and then our traffic will be routed to our green instance instead of our blue instance. So what are some strengths that blue-green offers? First of all, we have almost zero downtime because the traffic switches instantly to the newer version via the load balancer. We don't have to wait for a redeployment, which could take synchronously about maybe half an hour, in which we are unable to do really anything because we're waiting for our applications to spin up. It also allows us to have an instant rollback. If we switch to our new version, to the green environment, for example, and we see a lot of errors coming along and a lot of users calling us and saying, hey, I think you've broke something, it's also easier to roll back because the blue version is still active and it's still theoretically absolutely functional. The only thing it needs is real user traffic. We also have a real-world verification because both are genuine production environments. Both the green and the blue environment are scaled the same and can handle traffic the same. So it's not something that has to be scaled up or scaled down. Both of them should be resource-wise identical. And it also isolates our risk a bit because typical things that go wrong in deployments, like crashes or resource spikes, happen only in idle environments. So they do not affect real users because real users are still seeing the blue version instead of the green one. But it also has a few limitations. The first one being you have double the resource cost if you have twice the environments. And it also requires maintaining two identical production environments, and this can all be a bit costly. Also, the dependencies, like for example, a database migration is a bit tricky because every database migration has to support both versions at the same time. Otherwise, you would lose the ability to roll back, which is so critical in blue-green environments. Another tricky thing are stateful sessions like caches, and if you have long-running user connections, you can risk disruption to that. There are mechanisms to sort of terminate them gracefully, but if they are not in place, this is just a little bit of extra caution you need to take. And the last point is because traffic is switched all or nothing, that means if a bug somehow slipped through testing and didn't really come up until you have switched your whole traffic over to the new version, you roll back even if you say you are quick and you have just 1 hour of the wrong version running with a bug in it, then you would still have 100% of users at this time hitting your wrong and your bugged version, which is not, of course, not optimal because this can mean corrupted database entries or wrong user data, and there might be a way to sort of do this a bit better with a small little hack, which I call a mirror-first approach. And the theoretical idea is quite simple. We are shadowing our production traffic. We can tell our little helpers that they need to duplicate the live incoming traffic and route them to a newer version of our application. That's a bit like the dark launch that we've just heard. And it sort of combines the idea between blue-green deployments and dark launches. Also, what's really important, the mirror has to have a fire and forget execution. This means the response from the mirror can never reach the user, because you're testing this application and you're sort of need to handle the way in which the application, for example, just has a bug in it. And you want to spot the bugs and you want to see the bugs, but it's unhelpful if you send the messages out to the user anyway, because then you could scrap the idea entirely. Also, it allows you to test the new version against real-world data and volume with zero risk to live user experience, because users will still only see our V1 while the V2 is being tested, but no one has any clue that is really being tested, because we hide the responses and we hide the traffic, and everything just gets copied over to the next instance. I also have a diagram here. This is the same one that we have seen before. So in here, we are all on the application V1, the blue environment, and we have deployed our application V2 to the idle environment. And so far, all of our tests have gone through, and we would, in theory, be ready to switch the traffic over to the new application. And instead of just switching the traffic over to 100% to the green proxies and staying on the left, we add another shadowed instance. And this shadowed instance also receives 100% of the gateway traffic that comes along, but importantly, it doesn't share the same database as the blue and green environment. Because if there were some bugs and errors in the shadowed version, we would still corrupt our database, and that's not something we want to have. And after this has been successful and we can see, okay, our shadowed version works as expected, which is the same version that we plan on deploying to the green instances, we can then go ahead and delete our shadowed instance and move traffic over to the right, to the green instance, and have users hitting V2. So how does mirroring change the blue and green flow? The shadow phase silently processes copied live traffic before serving real users, and it validates the infrastructure against actual volume and behavior, catching bottlenecks synthetic tests miss. Also, the failures that happen in isolation. That means live users remain absolutely unaffected on the stable version because the other one is just isolated away. And the switch becomes more of a database decision than just sort of a leap of faith after your QA team has gone through. And then you can say, okay, my metrics, my logs, and my traces look fine. We have had a lot of users hitting our application that would have not normally happened in our load test because, for example, our load test only uses like 10% of real user traffic. And if that all works, you can safely switch over to it and you have a better understanding how your application could perform, because it's basically a hidden rehearsal of what would happen if you were to switch over to the newer version. But it doesn't help everywhere. In the cases where it's incredibly helpful is if you have services which are stateless and read-only. So something like search, recommendations, or data retrieval, where it doesn't matter if you process the same request twice. It's also fantastic for validating behavior under real concurrency and database load without risking the live user experience. And in my opinion, it's absolutely fantastic for refactoring verification. That means you have a piece of code that has been written in a legacy system and where you say, okay, this is either a bit slow or it's a bit buggy, and I want to make sure that the refactoring that I've done produces the same identical output. And the way that you would typically hear and typically go about is that you go ahead and you have your tests that go through. You have, for example, some load tests which try to emulate real user behavior, but it's not really the same. And there can be instances where a small little bug in an edge case, it's not tested, but a lot of users, for example, happen to do that by accident. And with this way, You can afterwards compare the outputs. You can go through the logs, which should be fairly identical. You can see the backup database, which should contain sort of the same entries. You can run queries through both of it, because if you mirror 100% of the traffic, the shadowed version will behave as if it weren't shadowed. But there are also cases where it just doesn't help. For example, it's absolutely not helpful for testing new features. Mirroring replaces the existing traffic patterns, and that means everything that you've added in your newer version that cannot be accessed in the old version cannot be tested. If you have a website and you add a new button on there, and you try to shadow the traffic over to your V2, no one in V1 will be able to hit the V2 button because it's just not there. And also you have to be a bit careful for external side effects. That means duplicate calls to third-party APIs like emails or payments. They occur as if it was a live application, and that means that every dependency must be able to be injected and must be able to be mocked or stopped. Otherwise, you would risk real user impact with duplicate emails, and like worst case, I think, would be a double billing or something, just because you've tested anything. But you cannot do it out of the box. There are some preconditions that you need to have in order to be able to pull this off. And the first one is you need to have a service mesh infrastructure. That means you have to have a Kubernetes cluster with Istio or something similar, and the apps must have sidecar proxies for traffic routing. If you try that without our little helpers, you won't really get far, because they just enable you the possibility to do these kinds of advanced traffic routing things. It's also important that you have a bit of spare CPU and memory to handle the combined load of 100% traffic, plus the mirrored shadow traffic simultaneously. It's another environment that you put up, and because you already have blue and green, you have two environments more, and you just need to be sure that mirroring and shadowing your traffic does not impact your cluster's maximum CPU usage to a point where you cannot handle it. Also, sort of the major idea behind this whole system is that you can see what's going on. If you don't have a good observability strategy, and if you don't have robust signals that you can compare to each other, and a good strategy of how you actually measure the success in there, it will be a bit difficult to go ahead and see if your application really works the way you want to. And for that, I have a sort of a practical demonstration how this could and should look in Octopus deploy and in code. So here is my mirror blue-green example, where we have an application that has 5 environments. It has a dev environment where you can deploy to, it has a test environment, and then before it would typically go over to prod blue or prod green, there's an optional mirror environment. And this optional mirror environment needs to be discussed if it's even helpful. As I've said, if you're testing a new feature, then this won't really help you. But if you try to do so and you have everything prepared, you know that the feature you're trying to test is a good candidate for that, then it all just comes down to how you configure it and you code it in Octopus afterwards. Let me just switch my mirror real quick. Okay. This should hopefully work. Yeah, as you can see here, we have our deployment. And in our deployment, we need to make sure that we have set up everything so that we can handle this kind of scenario. That means we need to be able to distinguish applications by the environment and by the color and by the app name. The app name is something that's typically in here, but the color is important for us to use. And also here, we said this is just done for a Node.js application. And Everything that's in here is posted to my GitHub, and I will give a link at the end where you can find all those files. Other than the deployment, we have, of course, the service. This is all just Kubernetes native. That's nothing new. That's nothing special for the service mesh solution that we have. But where it gets interesting is, first of all, the namespace, because we have to configure the Istio injection. That means that our sidecars will propagate our pods, and we have the ability to do the advanced traffic routing. And then we need to configure our subsets in the destination rules. And here you can see we have the blue environment, the blue subset, we have the green subset, and the shadow subset. All of them basically boil down to the label color blue that we have in our deployment. So we have labels color blue here in this variable. After we have our destination rule, we can reference it in our virtual service. And this is sort of like the key thing that handles traffic routing in a service mesh or in Istio especially. Here we have a service that manages our traffic based on the 7th layer. That means we can do ingress and egress, and we can handle it really, really outside and far of the stack. So we have access to a lot of information and a lot of tools. Here we have two different routes, and the first one is our route to our blue subset. This is just the path that you need to take to have in-cluster routing. And here is basically the port number or the container port that we want to use. And what's special here is we have two routes. We have our blue and our green route, but in here is the small little flag that says wait. And if we want to deploy to the blue instance, we can just say here we want to have a weight of 100, and we want to have here a weight of 0. And this we can do and switch on every deployment so that we can switch back and forth. What we have here is the mirror section that tells us this is the host we want to have with a subset shadow, and we want to mirror a percentage of that traffic. This can be 100%, this can be 1%. I don't think 0 makes any sense. But here you can configure basically the amount of impact that you want to have. And then the rest in here, it's just our Istio gateway. That's something that we just need to have here in order to tell the traffic where to actually be able to go and to route to our applications. And we have a peer authentication that's for MTLS. In this repo, you can find also the variables in Octopus form, which basically says what percentage should go where in which environment. And as I said, you can find everything that's on here at the end of the presentation in a GitHub link. So going back to our presentation. What are some gotchas and some pitfalls that we need to be aware of? The first one is, of course, the proxy overhead. The mirroring logic runs in the sources sidecar proxy, requiring it to serialize, copy, and transmit every request. That means we have to be careful that scaling something up doesn't affect our source application too much, because it's the source that eventually goes ahead and copies the traffic over, not the destination. And the source is the thing that we really need because it's the application that our users are hitting. The other is the latency risk. And it's basically just the consequence of the thing above, which means if we have a lot of packages and a lot of requests that come through our source pod and our cluster is not able to handle this kind of traffic, then it can be that we introduce a bit of latency or even drop packages. So the solution for that is that we must provision some extra CPU headroom for the sidecar containers and not just the app before enabling mirroring to prevent starvation. But that's something you can try out a little bit afterwards and just increase the value to a bit and see how much performance that really costs you. The other one is not only the CPU, but also the network, because copying traffic effectively doubles the package count leaving every pod. And this means you have to be careful if you're in the cloud, because if your mirror runs in a different availability zone, then all of a sudden you have a massive cross-zone data transfer. And this, of course, costs. And the third one is the solution for that, to basically go ahead and make sure that the mirror and the live targets are near to each other, so that you have as less latency as you can possibly have and as less network traffic that you need. Also, it's important to beware of the side effects in the mirrored version. The mirror version in of itself believes it is live and believes that every user request that comes through is from a genuine user and not copied. So if you have a dependency in there, or for example, an endpoint called charge credit cards, the mirrored version will absolutely go ahead and call that endpoint if you have not mocked it. So you need to be careful here, and you need to make sure that a lot of the preparations have been done for this and that you can do this safely. So as I've said here, you need to redirect the external dependencies either to mock servers or to something else, so that the consequences of those traffic requests never actually hit your users. Also, there's a cold cache bias. Typically, when you do a mirrored instance, you want to see the performance. But what you need to also incorporate is that your V1 is fully optimized. That means the caches are warm and connection pools are established, and your V2 starts off completely cold, because you should not really use the dependencies that you have in V1 for your V2 instance. Otherwise, the mirror could mess with your original version, and that's not something we want. That means V2 most definitely will initially appear slower and more CPU heavy. And this can lead to some false alarms where you can say, okay, that means my new version isn't as stable and isn't as performant as I thought it was going to be. And it can lead to some early decisions that might not really give the whole picture. So I think a mandatory warm-up period of at least 30 minutes to fill caches before even taking a look at metrics is always a good idea. Otherwise, you just get yourself down for something that's not even real, because V1 just had the benefit of being available and alive for a bit longer and filling its caches. Some key takeaways here are that mirroring blue-green deployments allows you to de-risk the cutovers. It means that this high-stress leap of faith deployments where you say, okay, I'm pretty sure that it works, but I'm not entirely sure, is a bit more data-driven and can help you make the decision easier. Also, it allows you to have real-world testing. That means you can safely test against chaotic production traffic patterns and concurrency without impacting live users, as long as you have all of the preconditions like the extra resources for that. But it also means you have to have a high maturity in your applications. That's not a free feature. It demands that you have the ability of having your software run in multiple versions at the same time. And this is, I think, exactly why it's so helpful with blue-green deployments, because if you can run blue-green effectively, you already have this kind of functionality. And always beware, this is a strategic tool. It's not universal. It's incredibly good for refactoring and tuning, but it's often an overkill or just invalid for something that you really cannot test. But if you can do this, that's always a fantastic feeling, because you get so much more insight in your testing strategies and your applications. So that just leaves us with the question, what else can you do with the service mesh? I've just given you a small exempt of the possibilities that you can have, and more of them include canary releases. You can shift traffic based on real-time health metrics. You can limit the blast radius, and you can even go ahead and filter traffic and route traffic based on headers, for example. This is what I've meant when I told that friend Steve should be able to be handled differently than anything else. You can have circuit breaking and retries done by your infrastructure, done by your cluster, without having that in every single application. So you can manage this once and for all. You can also do some chaos engineering with Istio. You can say, for example, that every request to this and this endpoint has a 5% chance of just aborting with a status code 500, or delaying for 1.5 seconds to see what's really going on and how your application will handle some edge cases like this. And it also allows you to have this zero trust security via MTLS, because you can encrypt the traffic and enforce the auth policy on Kubernetes level and on the infrastructure side. And this is my presentation. Thank you so much for having me. Just as a follow-up, my company and I, we are doing a webinar on the 15th of January at 4 p.m. Central European time that talks about compliancy through zero trust with NIS2 and Istio and all of these things, basically.